So thanks again, Greg, for that wonderful introduction, and thank you, everyone, especially to the conference organizers, for extending me the honor of kicking off our session with this keynote today. And before I begin, I want to acknowledge that the work I'll be presenting here, as all of us know, would not be possible without the tireless dedication of our graduate students, and so I want to especially acknowledge Karen Angelis and Rachel Hamburger for the contributions they made to this presentation. So I don't need to motivate to this audience the importance of mitigating the damaging effects of extreme wind events. However, we've had a lot of newfound urgency around this topic in recent years, especially in the United States. So much so that NOAA has now coined a term called the billion-dollar event. This graphic was released in 2020 to open our eyes to how many of the discrete climatological events that were occurring in the United States that were each causing $1 billion or more in losses. So the effects of these events started to compound so fast that you couldn't complete the recovery from an event before the next one would strike. So setting this goal in the United States of this life safety objective for codes and standards meant that all of a sudden we were starting to absorb a mounting number of losses, especially to events like hurricanes. Now we have an insurance industry that's collapsing. FEMA is officially out of money officially by the end of this month, well before our first hurricanes have officially struck in the Gulf. And in short, we no longer can absorb taking these losses. So our communities actually are the only living laboratories, the only place where scientists and engineers can actually come to study the complex interaction between the natural, built, and human systems during an extreme wind event. And as such, as devastating as these storms might be, within them holds the opportunity to learn the valuable lessons that will be central to reversing the mounting losses countries like the United States and others around the world are facing. So I like to talk about what we do to learn from these cycles of disaster, what I like to call the disaster data to knowledge life cycle. It begins with collecting field observations in communities to document the impact of these windstorms. And the vulnerabilities that we see during those investigations, well, those then inform the kind of research and development activities that we need to do if we are to address those deficiencies. Now, this might result in new mitigation strategies, changes to our codes and standards, maybe new innovative materials and systems. But the most important part of the cycle is the effective translation of that knowledge back to the communities, guiding their efforts to build back better. But as we're learning quickly in America, we actually need to build better before. So my talk is going to especially showcase how we're leveraging some shared infrastructure to do this work in the United States. You might be familiar with the Natural Hazards Engineering Research Infrastructure. It's called NARI. And it's supporting a lot of the work across this cycle through shared resources. In particular, my work today will highlight how we're benefiting from more effective coordination of these field investigations through organizations like STEER, which I help to co-direct, as well as getting access to the equipment we need to canvass these areas efficiently through what's called the RAPID facility. And you will also see today how the evidence that we've gathered in those investigations is being strategically leveraged through computational infrastructure that's provided by the NARI Simulation Center, or SIM Center. And all of this takes advantage of a cyber infrastructure that kind of links the whole network together called Design Safe. And you're going to find all the software and data that I talk about today is actually available for you to use on that platform. It was, in fact, the idea that we now had all this access to resources and shared data and models that really started to pique my interest as a researcher in how we could actually link this cycle to accelerate the discoveries that we could make together. So I'm going to use this cycle as the organizing framework for my talk this morning, and I'm going to provide vignettes to you about, what we're learning at each point of that cycle. So first, we're going to discuss how we actually more efficiently move through a disaster-impacted area by deciding which routes to literally drive a car to collect those field observations. We will then consider how those field observations can be efficiently aggregated to, extract the damage levels that are observed. And then how those can in turn be leveraged to generate observation-informed fragilities unique to each affected area. And then when combined with regional simulation tools, how we could actually communicate the impacts to individual properties, even down to the component level of losses, and do so in a very computationally tractable way over entire communities. So let's get started at the first stage of the cycle. And now we consider the idea of how we automate route selection. So you might wonder, what does that mean? Well, in the wake of a major wind event like a hurricane, there is a need to efficiently gather perishable data, which is basically the forensic evidence that we use to understand how well the building codes might have performed or how our construction practices actually need to be refined, and at minimum, just to document losses. But these areas are huge and they're very challenging to navigate after these storms. And you know that as soon as people start cleaning up, you lose the evidence that you're trying to capture. So that really limits how much data we can actually get to in a fixed amount of time. So fortunately, there's some new technologies that are coming out, some things like called street view cameras that are enabling us to image these areas very efficiently. And so what we're working to do now is try to automate that process of how we move through an affected community with these cameras to capture that data. And some of the algorithms I'll be talking about in this particular snapshot are available to and were discussed in our Extreme Reconnaissance Network, or STEER, report on the Hurricane Ian, which you can find here on Design Safe. So as I mentioned, Google has a technology called Street View, and you might have used the Street View capability in Google Maps. And what we found is it's an incredibly useful technology to image an area after a major wind event. So in STEER, our network, we are actually using it as the first part of our reconnaissance efforts. And basically what happens is you drive the vehicle through these areas, and the data that's captured by these camera systems can be immediately uploaded into Google Maps or platforms like Mapillary so everyone can access them quickly. Now, we would typically put the camera system on top of a car, but we have put it onto boats, on drones. We've even worn it on backpacks to access areas that are difficult to navigate. And all the green lines that you see on the map behind me, those are the routes that were driven in Louisiana after Hurricane Laura in 2020. And the little video that you see running there are examples of the imagery that that car is capturing as it's driving through that area. So we saw how advantageous this was in Hurricane Laura, but we wanted to find out how we could use this more strategically. So to do so, what we wanted to do was say, first of all, let's characterize the entire domain that was impacted by this event. Let's map all of the building footprints and all of the roadways. Let's pull all the information on the windstorm itself in terms of the hazard exposure and all that we can know about the buildings in that impacted area. We would query all this from places like a tax assessor database where much of this information is housed. Now remember, we have to get these vehicles on the road within 24 hours of the hurricane. So as a result, all this needs to happen in a very automated way and very quickly. But it also has to be flexible to adapt to situations on the ground. So we began a process of a multi-objective optimization. It parses a broad set of clusters to give us our first instincts on where we might direct these vehicles. And the Pareto-optimal solutions that come out of that algorithm will help us figure out how to do so while minimizing our drive time. Then we can take those clusters in and do a constrained single objective optimization to refine the cluster to specifically pick literally what roads we will drive for whatever objective we have. So if the goal of the mission is to get all of the houses that were built in a certain, let's say, year or certain edition of the code, we can literally optimize for that. And then once we found the neighborhoods that would give us that information, we can then go through the Google API and literally get the driving routes we should send our drivers onto to get that data as efficiently as possible. So let me show you, we've run this for a number of wind events, but let me show you a case study for Hurricane Michael in 2018. So let me illustrate the process and show you, first of all, it starts with a big map of the state, showing all of the data that we collected. You have your best track with the wind swath giving you your characterization of the hazard from the National Hurricane Center. We have the census tracts coming from U.S. Census Bureau, which gives us a very coarse description of the building inventory. And we're interested in any clusters that are in contact with that wind swath. And then we're going to extract for each of those clusters how far it is from the track, what's the exposure level it received, and what's the size of the cluster and the density of the buildings within it. And then we'll use those as our decision variables to optimize and select which of these many, many clusters within the track of the hurricane we should focus on to get those that were most exposed to the hurricane, have the most buildings to survey, and minimize the drive time. So now that you've kind of picked those more coarse clusters to focus on, we have to get a little more refined in that process and kind of pick a few to begin with. So we have that feature vector, and that lets us start an optimization process. And the Pareto front then lets us determine a subset of the most optimal clusters that we should visit during our mission if we're going to collect the best set of data possible. Now, there's an advantage at this point to actually giving our driver multiple options to pursue from this first step in the optimization, so they can adapt in case things change on the ground. But let's say the driver has no preference, then we would naturally move toward the utopia point and present that cluster as a starting point for the algorithm and direct our drivers to go to that location. You could see it in orange there on the map. So now once you get down to that coarse cluster, it's still pretty big. And figuring out where to find the buildings you need to survey is quite challenging, so we narrow it down even further in this next step. And so what we'll want to do is find the exact neighborhoods that car needs to drive. And we usually do that through one of two ways. We set the objectives for the mission. So one class of objective, again, might be get me all the buildings that were built at a certain year so I can see the effect of the code in that year. And we might optimize to find, let's say, all the houses built to a certain year of construction. Or we might say, find me a representative sample. That means take me to a neighborhood where I'm going to see the same proportion of residential, commercial, schools, critical facilities, the same distribution of these important classes that I would see in the overall inventory. So we could optimize for any number of mission objectives. And we can bring in all the roads from OpenStreetMap and all of the data on these buildings from the Department of Revenue for that state, in this case, the state of Florida. And that lets us create some new decision variables by aggregating these data sources and then optimizing with this new, more refined information. And that more finer optimization process can now optimize for specific classes of construction and specific occupancies to pick where we should specifically drive within our course cluster. Now again, cost is going to minimize the entire process. That's our constraint. So we're looking to minimize drive time. And normally in a single day, we can drive anywhere from 50 to 100 miles, depending on the traffic condition. So we would set a constraint like that on this problem, and basically the algorithm will give the driver as many possible routes until that quota is met. And again, it will just optimize based on those conditions, finding the houses of similar age based on the variance within the cluster, or finding a representative sample by minimizing the Euclidean distance between the distribution of occupancies in the cluster and the overall inventory for the state. Now, at this point, the algorithm gets a little nerdy because eventually you're going to start talking to Google to figure out what to do. And I won't bore you with all the details of how we use that API, but essentially we ask Google to connect the dots for us and find us the optimal driving routes to cover the clusters that have been selected in the second stage of our algorithm. And so what we like to do at this stage, I would not run this final execution of the Google API until right before we leave the door, simply because it will update for the latest traffic conditions and closures, which are plentiful after a major hurricane. But literally, once you interface with this API, you would get the driving route you see on the right side downloaded to your phone, and it would tell you how to navigate that area to optimize the data collected. Now, if you actually take a look at how this would have changed the way we approached an event like Hurricane Michael, well, it has a big impact. The red lines that you could see were the original routes driven by our steer team, and that was a human making the decision to work along a major road across the hazard gradient. Had the optimizer been available in 2018, it would have actually told that person to drive the cluster inside the orange box and that blue road and would have obtained a very good representative sample. And if we wanted to move along the hazard gradient, then simply at step one, we would have specified additional course clusters later on down the coastline, if you will, and it would have optimized the routes within each cluster to get a better and more representative sample rather than just picking the utopia point. I guess the end result that you can see is with this newfound data capacity, we could revolutionize the way that we attack the collection of this vital data after major hurricanes. So now we've got imagery from an affected area, and we need to consider now how automation can help us at the next step of the cycle. and that is linking that imagery and actually turning it into quantifications of damage. You see, that imagery is coming in, but normally in any of our missions as an organization, we are having humans assess that photograph and translate that into a damage rating. So the ability to run through hundreds of miles of roadway is powerful, but that leads to thousands and thousands of images, which is way too much for a human to assess. Now, the good news is the data science community is making a lot of algorithms that are freely available to help us with these kinds of image detection tasks. So, given the large amount of data that we've been collecting over the years in networks like STEER, that actually gives us a nice piece of training data that we could use to get these algorithms up to speed and to become our helpers in this process. So let's see how we could leverage that in going forward. So in our next vignette, we're going to look at an interdisciplinary project that's actually taking place under what's called the Strengthening American Infrastructure Program. It focuses on housing. Housing is the biggest part of the inventory and unfortunately sustains the most damage in hurricanes. If we want to reverse this trend in the United States, it means we have to convince homeowners to design their houses above the code and to do so voluntarily. And that means understanding how you influence homeowners. And we just wrapped up this study in Lake Charles, Louisiana. Again, that is where Hurricane Laura occurred in 2020. That was a design-level wind event. It had very high damage rates across this inland community of Lake Charles. You can see the orange and red plots here. Those are signs of houses that were severely damaged or destroyed in this hurricane. And we wanted to optimize which houses we talked to with this survey, in the same way we're trying to optimize which structures we survey after the damage event. After all, it's very expensive to talk to humans, and we need to guide those resources very carefully. So we wanted to create a representative sample of this community, both demographically and with respect to the damage sustained. And that meant we needed to figure out quickly which houses were damaged or undamaged before we deployed our survey instrument. So we took the data that was available from NOAA. These are aerial images that they take over major hurricane zones. And we wanted to do a quick roof classification algorithm to figure out the damage based on that imagery. And this was a binary classification model, simply flagged a building as damaged versus undamaged. So we took a pre-trained neural network, retrained it with all the available data from the STEER network, and basically took that labeled data to go ahead and train this algorithm. And the confusion matrix that you see at the left side shows the performance in the classification task. You should see ones on the diagonal if it's doing a good job. So you see a 95% accuracy in detecting a building without damage. And you see that drops a little bit to 85% for buildings that are damaged. The off-diagonal terms show the false positives or false negatives. Now, that reduction in performance that you see for the damaged buildings, that's due to the things you're seeing in the images on the right. Occlusions, meaning trees or other things blocking the image, shadows, a misdiagnosis of a structure, or simply roofs that have a very minor level of damage. And those examples illustrate that these algorithms can sometimes struggle in binary classification. So in light of these errors, and given the fact that roof damage doesn't necessarily show the full extent of other types of damage to the structure, including water penetration, we also automated an algorithm to get all of the permits that were issued in this location after Hurricane Laura. And that would indicate to us that reconstruction was taking place. We then fused together the permit data and our roof classifier, and if a building is positive for either of those indicators, it's flagged as damage with a red flag in the data set. And then if it's not, you see it as green. Every single property in the entire parish of Calcasieu, where Lake Charles is located, was actually tagged in this process. And that let us then create a stratified sample that demographically represented the community and with respect to structural performance represented the community. And then we sent out 26,000 surveys to understand how those families were responding before, during, and after this hurricane. Now, as we were waiting for their responses to come back, we started working to refine our visual classifier. You see, with all this data available through networks like STEER, we could actually start to train even more advanced rooftop detection algorithms. And we could create some additional classifiers that would weed out these troublesome situations that cause these classifiers to fail. And that can be achieved by actually bringing together two sources of data. taking the images from those street cameras that I talked about earlier and combining them with what we can see from above. And that way we can tell if things are being blocked by trees, or more importantly, determine if a structure has collapsed or completely lost its roof, in which case we wouldn't want to bother doing a more refined classification because it's already clear what's happened there. Now, this let us really shift our computational power to much more complex tasks and improve the fidelity of our estimation. So we reshaped our entire algorithm to basically go through this process, to improve that classification and make it more granular. And the idea then took all of these available information sources, combined the street view and aerial data to do a first classification to weed out, again, any troublesome images, and then move that a step further into what's called segmentation. That means identifying not just the presence of damage, but the specific nature of the damage to the roof. So we could have a much more representative picture of what happens in a community very quickly for the use of both this type of study and other applications. So this shows you what segmentation can do. This single slide shows you that what we could take is a roof image and through segmentation could distinguish what is roof cover, what is underlayment, what is tarp. That lets you literally count the number of pixels associated with each of those types of cover, if you will, or rooftop feature, and be able to segment them. So we're using what's called a YOLO V8 segmentation algorithm. It was retrained using existing reconnaissance data and is able now to pick apart pixel by pixel all the features on that roof. And that gives you much more granular perspective on damage. Where we're taking this further now is getting down to literally seeing identified like exposed joists and other features. So we can really literally pick apart the layers of the roof and get the data down to that much more granular description, much better than just damaged or undamaged. So now that we've shown how we could optimally capture images through a large area impacted by a major hurricane, and we can even automate algorithms to then process that imagery to detect the levels of damage down to a fine quantification, we can consider how to take that information into the next stage of the life cycle. Loss modeling. It's got a lot of attention in the United States given this alarming trend of losses that are mounting and the need to start targeting mitigation investments. So this means we've got to start characterizing risk much better than we've done and do so over inventories of buildings that are always evolving over time. So as much as we are working to improve our ability to describe the building inventory, we don't have many fragilities to actually capture all the types of building practices in our country. And those, again, are evolving continuously. In fact, the fragilities that we do have are associated with generic building models, what we call archetype structures. And they were assuming a certain style of construction and a certain edition of the building code when they were conceived. And that may not be what the actual buildings look like in a given region, who have regional construction practices or were built to different editions of the code. So the question becomes, could we take all this data that we have now and actually develop libraries of fragilities that are calibrated to specific regions and continually updated as new storm events unfold? Well, we wanted to try to do so through a Bayesian approach that actually does that updating with all the storm data that's coming in from our reconnaissance efforts. And you can read about this more in our paper in structural safety, but let me briefly step you through the concept. So the idea is as follows. You have this building inventory of interest, and for each building in that inventory, you need a fragility description that captures how similar buildings have performed in past storm events. So we'll need to find a sample that is representative and then get all the post-disaster data for buildings in that sample. And after we do that querying, then we would be assembling and fusing all that damage data together, along with some description of the hazard, and use that to basically construct fragilities that we would update continually through a Bayesian scheme. Now let me take you through the steps of how this is done because it gets really messy with real data. So let's go back to Hurricane Michael, the panhandle of Florida. First, we'll pick the type of structure that we want to investigate. So let's say we want to look at single-family homes, very common in the United States, made of wood, and they often use asphalt shingle roofs. Let's say we want to adopt HAZIS's hurricane loss model and use its damage scale as our damage measure. That's a 5-point scale. So what we're going to do is go into that area and have our algorithm go and pull all the disaster permits that were issued in the state of Florida for this hurricane and all the assessments that were done by humans through our STEER network for this campaign. And you will see the total number of buildings that we have in our sample, nearly 6,000 from those data polls. Now we've got to dig through those 6,000 buildings and figure out which ones we should use to calibrate a fragility. That is actually really challenging. So here's how we navigate that in an automated way. We create guidance for the algorithm to make good judgments. And here's how we do that. We first tell the algorithm, find all the buildings that have the same occupancy, find all the buildings that are using the same structural system and the same material of construction, in this case a wood frame, and were built within the same year of construction. So it goes out and finds those. Then we say, what component are we focusing on for the fragility description? In this case, the roof cover. Okay, well, what variables or what geometric features of a house actually dictate the performance of the roof cover? Well, if you look at AAC7, components and cladding section, you'll see that usually those things would be dictated by the roof pitch, the roof shape, and the building height. And more importantly, if you look at the descriptions of the pressure distributions, you'll see that they have a range for which they don't really change. And that gives you a range then of geometric features that you can use as a search condition to make a more relaxed criteria to find the sample buildings that you can use to construct your fragility. We would also ensure that the building was impacted by wind and not storm surge or other factors. So basically what you do in this algorithm is in the column that is blue, you specify your target building, the building you hope to model. And in column purple, you set the range of acceptable values for any other companion building in the existing data sets that would be a good match to this target building and therefore a candidate to build the fragility. All right, well, when you do so, you actually find a lot of buildings that are similar in Florida. Take a look at this. So if we go to Bay County, Florida, where Hurricane Michael impacted, you will see that we are able to find quite a few homes that hit that condition. In the first column, you're going to see homes that were built before the Florida Building Code took effect. And in the second column, you'll see the ones post Florida Building Code. We also were able to pull two interesting features. All the homes that have their original roof, that's the first row, and all the homes that were re-roofed. And that's an interesting point. You don't care about when the house was built. You care about when it was re-roofed. So we pull permits to figure out the last time a roof was replaced, because that'll be critical to see how it actually performed. So you can see the samples for all those 4 different categories on the beach, and the wind contours are there for reference in meters per second. So now we have all the buildings in the sample that are eligible. We have to find out what damage information is available for them from all possible sources. Again, we pull permits, we pull FEMA, we pull STEER records, anything that we can find. But then you've got to fuse that data onto a common scale so it's usable. And that's quite challenging. So we made a data utility index to guide the algorithm in making sound judgments on what data to fuse and what data to discard. In general, field observations by engineers hit all of the metrics for data utility because they're collected by engineers right after the event, and they use quantifiable damage scales, in this point a 5-point scale as specified by HAZARD, so it's very quantifiable. But when you're pulling other data like permits, it's a qualitative data, it's narratives, it's words written by non-engineers. So those have to be translated into damage descriptions and mapped back onto a scale similar to what an engineer uses in the assessment. That takes a lot of effort. So we had to write translators to basically interpret what a building permit says and turn it into engineering judgment. But once you finish that process, you can actually now create a damage failure set. You get all the damage unified on a 5-point scale. You then connect it to the wind speeds that were hindcast after Hurricane Michael, and suddenly you can start to develop those fragilities. You now have damage pairs, and you can separate those out again for the houses built before the building code and after. So for example, at damage measure 1, which is minor roof cover loss, we have all the buildings that have 2 to 15% loss of roof cover from all data sources. That's 500 homes that were built before the Florida Building Code. And what I also want to point out is by widening our willingness to use data from permits, we are able to really expand the number of samples available to calibrate that fragility. So even though it's a lot more work to translate written words into engineering numbers, it actually pays off. And then we can actually use these to construct the fragilities and do the updating. So we take the fragilities that exist in HAZAS, which is our common loss modeling environment in the United States, that's the black line. we treat that as the prior. Then we update the fragilities based on the observations in Hurricane Michael. We do so for all the homes that were built before the Florida Building Code, that's the red, and after the Florida Building Code was enacted, that's shown in blue. And as you move across this chart, you'll see damage states increasing from damage state 1, minor, all the way up to states 3 and 4, which are full loss of roof cover. Now, what you can see also is the top row is the houses with their original roofs, and then the bottom row is the houses that have the re-roofing done. That means they've had permits issued and the roofs completed. And you can see how the fragilities are adjusting to show the improved practices that result from the enactment of more strict re-roofing guidelines in the state of Florida. So in general, what this gives you now is a framework to continually update fragilities based on damage observations as they become available in these reconnaissance missions across the United States. So now, we have automated the way we drive through communities to collect the data. We can process all those images rapidly and even bring that data into descriptions of fragility that are region and even component specific. But now we have to bring this all together to communicate risk and close the life cycle. Now, many of the established loss modeling environments that we have in the United States and around the world were meant to aggregate building portfolios and look at more generic building classes, largely because they're created for insurance purposes. Yet, when we're trying to talk to stakeholders now, they want to know the cost benefit of specific mitigation investments on specific structures. So we have to model at a finer level. Thankfully, there's a lot of open source software and access to high performance computing that's making that increasingly possible. And those models provide the computational scaffold to begin that process, but you still need the middleware to translate that scaffolding into a given region. So now I'm going to show you how you take these open source tools and bring them into a specific location. You can read more about this in our new paper in the International Journal of Disaster Risk Reduction. But let's go take a look at how you now can run a regional loss model. So we're taking advantage of an open source software called the R2D, the Regional Resilience Determination Tool, which is available from the NARI Sim Center. It has a nice user interface and a very beautiful back-end modular workflow. What this allows the user to do is easily execute a regional simulation of a wind event. Think of the backside of this as puzzle pieces. You can pop different pieces in to change the workflow easily and then just press a button to run it on high-performance computing. Now, we've built 2 test beds on this platform that you can use. One is for the areas affected by Superstorm Sandy in New Jersey, and the other is in the areas affected by Hurricane Laura in Louisiana. And both of those adopt a HAZA-style approach. But what we want to do now through this example is actually show you how to update 2 puzzle pieces. How do we extend this kind of model down to a place like Florida, which has a very different code environment? And how do we bring in then those new fragilities I just showed you to enhance the accuracy of the description in those locations? So to start, we would have to come into a brand new place, Bay County, Florida, and describe every single building in that inventory and map it to a building class. In HAZUS, that means finding one of 15 building types. So you automate algorithms to go scrape all of the tax data and figure out what each building is made of, how many stories it is, and what is its occupancy. And those are the 3 pieces of starting data, and you can scrape those online. But now you need to describe specific attributes of the building, because to assign a fragility, you need to know more than just what kind of building it is. You need to know, for example, what is its roof-to-wall connection. That is something that the tax assessor will not tell you. So what we've done is actually created some elaborate rule sets. What they do is actually take codes and standards, existing inventory data from national surveys, and even human data to understand if people use shutters during a hurricane. All this goes into actually creating a model that can assign all the properties necessary to be able to give a proper fragility description to every single building in Bay County, Florida. So the way this works is we actually create these rule sets for every edition of the building code in an area. And using the various logic that that code has over the many editions, you can figure out what a building most likely was made of based on when it was constructed. And what's interesting is you can even capture very unique regional differences. So for example, In the state of Florida, there is something called a panhandle exemption. What does it mean? The houses where Hurricane Michael impacted did not have to adopt the required windborne debris requirements. That got them out of that requirement to their unfortunate loss. You can capture those opt-outs through that red logic you see there, so that each of these rules will look at the location of the building, the year it was constructed, and figure out exactly what it was probably made of based on the code that was enacted at that time. So once you build up these rule sets, they become very powerful logic to guiding the algorithm to specify the properties of every building in the inventory. And all of ours are freely published in Python on DesignSafe. So now you can load that into the puzzle piece on the R2D platform and literally run the entire inventory for Hurricane Michael. We'll do single-family homes again, because that's the big loss driver. And for a single-family home, there are 5 attributes that you need to know about that house in order to give it a fragility description. So for those 2,244 homes on the beach there, we are able to specify those using these rule sets. And what we're also able to look at is 3 of these properties actually changed based on a new requirement that if they had a roof replacement after 2009, they had to use a more strict version of the building code. So we'll see if that policy actually helped things in this community. And to show you the importance of considering regional construction practice, we'll compare running this algorithm with the default rule sets in the SimCenters tool, which are based on International Building Code and International Residential Code, against the ones specific to Florida, using the Florida Building Code, and considering this new requirement for re-roofing after 2009, to see if those policies have any impact. So here's the summary in the most simple way I can present it. We are summarizing the total loss, the loss ratios totaled up over all 2,244 homes in this area. And here's what you can see. When you bring in the stricter building codes of Florida and represent them properly in your loss model, the losses drop by about 5% just for roof cover alone. So that shows you the importance just for one component of the building of getting that modeling right in your loss model. And if you enact the additional requirement of checking if that house had the roof replaced after 2009, you actually see another 5% reduction in the total losses in the inventory. And again, this is just for the roof cover. So it really emphasizes the importance of us moving past these generic loss models and toward loss models that are component-based and region-specific if we want to be able to communicate to a policymaker the impact of new legislation like this. Now, those loss models were still based on using generic fragilities defaulted in HAZUS, again, our standard loss modeling software in the United States. Those fragilities were the black lines I talked about earlier. But I can also update a second puzzle piece in the algorithm and rerun the whole simulation now not only for the proper inventory, but the proper fragilities for this region. And by doing so and rerunning the simulation, you can see the effect of bringing in those new fragilities calibrated to the observations we saw in Hurricane Michael. And by doing so, we can see how this evolves. So instead of looking at the loss ratio as a marker of performance, let's look at the actual damage state assigned to each building to see how it changes for the property of roof cover when we bring in those more localized fragilities. So what you'll see is HAZUS, which is the orange bar, would have assumed that most of the houses in Panama City had a damage state of number 1, minor, and in Mexico Beach had a damage state of 3 or 4, which is total loss of the roof cover. But when you bring in the regional fragilities, you actually see the roof cover losses were much less. They were almost 0 for many of the buildings in Panama City, and for Mexico Beach, you actually saw it was damage states 1 or 3. So again, you see that stricter code environment in Florida actually showing you that we were over-predicting the losses using HAZUS, and it really warrants bringing in those more regional perspectives. You can see that this R2D platform gave me a very efficient way to run a regional loss model 5 times in this simple example, all from my desktop computer. So this keynote has taken you through the entire disaster to knowledge lifecycle. It demonstrated how we could automate the selection of the routes that we drive to collect data after a major hurricane. and how we could then automate the way that we process all that imaging to figure out the damage levels to those buildings, and how that automation can help us update our loss models so that we have more regional fragilities describing local construction practice, and how we can bring that into regional simulation to communicate damage down to the individual building level and communicate risk in the way that stakeholders could actually understand. Ultimately, nothing that I shared with you today would be possible if we had not invested in sharing research infrastructure and sharing all that post-disaster data that we generate. The more proficient we become in taking advantage of all this open data and sharing it, the more we can speed up that cycle and make it information rich. And ultimately, that means we can speed the knowledge that we give back to communities when they need it the most. But to do that, we need more data. And we will start to leverage any and all people who can provide that data. I will take data from anyone. They don't have to be engineers, as long as they're willing to share. And we need to do our part, everyone here in this room. We need to create a culture where we share our data and our models in open repositories, and we document that data well so others can reuse them, as I have today. And finally, we have to take the extra effort to talk about risk and the root causes of vulnerability in very specific terms. And we must transfer those knowledge back to the people who ultimately make those decisions. We take a lot from communities. We take their data. We tragically tell the stories of all their failures. It's our responsibility now to give back that knowledge and to learn how to communicate our findings back to them so we can reduce their risk. Because when we do so, we actually become partners with communities, and they will then, in turn, share more of their data with us. So I thank you for the honor of being a keynote speaker at this important conference. And I thank all of you for everything that you do to help reduce the toll of wind losses around the world. I'd like to express my gratitude to the U.S. National Science Foundation for the many awards that supported this work, as well as to the American Society for Civil Engineers. I thank my partners who walk with me every day in organizations like STEER, as well as the SIM Center and the Rapid Facility of NARI. And most importantly, I thank people like these, the engineers who go out on the coldest of days to collect perishable data after disasters using organizations like STEER, and for those of us who use the data, who augment it and give it back to the community on platforms like DesignSafe so we can share and learn together. And with that, I think we'll have a discussion and some more questions. Thank you.